So very good evening. I beg to Dr. Kalaruddin. So today my group set of three people, me, Jingling and Emilia, gonna explain and do video about experiment I with benchtop cooling tower. So basically the introduction is cooling tower is a heat removal device that uses water to transfer processed waste heat into the atmosphere. All cooling tower operate on the principle of removing heat from water by evaporating a small portion of water that is recycled through the unit. The mixing of warm water and the cooler air reduces the latent heat of vaporization, causing a cooling effect to the water. In the case of laboratory unit, the water heater provides process load. It allows the speed of the fan used in the cooling warm water and the pump used to return the cool water to water heater. The experiment will be conducted by changing one of the element and remain the other constant. So we will change the three things, which is speed of the fan, cooling block, and the airflow rate. Then the theoretical, this cooling tower experiment operates according to the first law of thermodynamics, which is energy is conserved. Energy cannot be created nor destroyed, but can transform from one to another energy. The energy enters the cooling tower is type of heat energy. The data of the both entrance of the temperature was recorded. The formula used is H is equals to U plus TV. This formula is related to the temperature used to calculate the enthalpy of the system. The pressure is too low that we can assume it as ideal gas, which is delta H is equal to Cp delta T. Delta H water plus delta H air is equal to 0. It is proved by the law of thermodynamics. So next, it is detailed operating procedure, which will be explained by Ying.
Thanks to Joshua Dr. D. My name is Loo Jing Lin and my metric number is 199181. Today I'm going to explain about the detailed operating procedure for the part 1, which is variable air flow rate. First step, the benchtop cooling tower should be prepared, start, and allowed to stabilize under the following suggested conditions. The aurified differential is 15 mH2O. The water flow rate is 40 grams per second. The cooling load is 1.0 kW. Please note that stability is reached when there is no further appreciable change in temperature or flow rate. The second step, at regular intervals over a measured period of say 10 minutes, all temperatures and flow rates should be noted. At the commencement of this period, fill the make-up tanks to the gauge mark with distilled water. At the end of this period, refill the tank from a known quantity of distilled water in a measuring cylinder. By difference, determine the quantity of make-up which has been supplied in the time interval, and repeat the observation for different airflow rates. And part 2, which is the different water flow rate. And all the steps are similar with the part 1. The only difference, which is step 5, just repeat the observation for different water flow rates. And for part 3, the different cooling load, the first step is the same as the part 1 and part 2, but it's different starting from the second step. Okay? While keeping the water and air flow constant, the load should be increased to 0.5 kW. And when condition has stabilized, the observation should be repeated. Step 3. Similar tests should be made with cooling loads of 1.0 and 1.5 kW. If required, the fourth test may then be repeated at another constant airflow. And the last operating procedure, which is shutting down. Reduce the level in the make-up tank to about 50 mm by running normally. Switch off both heaters. After about 2 minutes, switch off all power supplies. If the unit is to be idle for several days, it should be continuously drained. Okay, how does the benchtop cooling tower work? Benchtop cooling tower unit includes a pump that impels hot water from the tank to the manifolds located at the top of the cooling tower. The water flow can be adjusted by the manual reserve valve. A temperature sensor located at the top of the unit measures the temperature. of water, and the water cools down as it falls through the manifolds of the tower, and finally falls into the tank, where its temperature is measured again. A fan propels atmospheric air with an accurate control of airflow. The air passes through wet bulb and dry bulb sensor before entering the column, and as air flows through the column, its temperature and humidity rise. With, on the another hand, the water temperature flows. Okay, at the upper side, there are another two dry bulb and wet bulb temperature sensors. Okay, what does the cooling tower do? The cooling of hot water was in the form of forced convection, by which ambient air was blown over the hot water and exceed the cooling tower at some temperature. So this is the result table. The T1 and T7 is always the same. This one is for the water flow rate. We change from 40 to 30 and to 48. And for the orifice differential and cooling loss, we will specify. And for the last part, which is part 3, we fix the orifice differential and water flow rate, and we only change the cooling loss from 1 to 0.5 to 1.5. Okay? And for the part 1, from the part 1, yeah, just now I forgot to mention, for the part 1 experiment, we specified the water flow rate and cooling loss, but we changed the orifice differential from 16 to 20 and to 24. Okay, that's all from me. Thank you.
Okay, now we'll proceed with discussion. The experiment was conducted to determine all the end-state properties of air and water from water charts and tables, and to study the effect of cooling loads on the weld bulb approach. Water needs to always added to the system because it acts as a coolant which removes heat. It will also absorb a high amounts of heat which can decrease the temperature of the system. This experiment consists of 3 parts, which is part 1, part 2, and part 3. Part 1 was conducted with a variable of air flow, constant water flow rate, and constant cooling load. Test 1, the orifice differential is 16 mm, test 2 is 20 mm, and test 3 is 24 mm. From this experiment, we found out that the increase of the airflow caused the increase of the makeup rate. In test 1, it increased by 135 kg, in test 2, it increased by 325 kg, and in test 3, it increased by 550 kg. This is because the increase of the water flow rate caused the water to evaporate more quicker, so it caused the increase of the makeup rate. In part 2, it conducted with a different water flow rate, constant air flow rate, and a constant cooling load. Test 1, the water flow rate is 40 g per second, test 2 is 30 g per second, and test 3 is 48 g per second. From this result, we can conclude that we found the result that the increase in water flow rate caused inconsistent reading in makeup rate. Next, for part 3. Part 3 was conducted with different cooling load, constant water flow rate, and a constant air flow rate. Test 1, the cooling load is 1 kilowatt, test 2 is 0.5 kilowatt, and test 3 is 1.5 kilowatt. From the experiment, we can also get the result of the increase of the cooling load caused the inconsistent reading of a makeup rate. The increase of the cooling load caused the inconsistent reading of a water outlet temperature also. From the experiment, we found lots of error in the experiment caused by a human's error and a system's error. The error is caused by IS not parallel to the scale of measurement tools, which affect the makeup rates and the pressure drop across packing. And student ordered to collect the data in an accurate time given, which is 300 seconds, that caused an error to the result taken. And the last but not least, the pressure in the cooling tower was inconsistent, that caused an inaccuracy in the result obtained. To proceed with the conclusion. In conclusion, the experiment is successfully conducted when the value of the power increase, the temperature of the cooling range in the cooling tower will increase. The higher the water flow rate, the lower the energy in the form of heat transfer or release, and the higher the power, the lower the energy transfer. All the objective was achieved. All the end-state properties of the A and water from the charts and tables and the applications of the steady flow equation to select the system to draw up energy and mass balance was determined. The effect of cooling load on the wet bulb was determined. That's all from us. Thank you.